whenever we go to make a measurement, we need to have some idea of the uncertainty or errors in that measurement so that we know how good our measurement is and what kind of decisions we can make based on that measurement. So this thermometer here, I've turned it on and it's settled into about 23.8 or 23.9 degrees Celsius as an indication of room temperature. And so we've got a reading, looks like 23.9 degrees Celsius. Now, I'm not sure whether that's the right value or the wrong value. Let's check at least. If I warm it with my fingers, oh, the number goes up. And my sense of the room that I'm in tells me that that's not a stupid number. So 23.9 Celsius makes sense. And when we warm it, it goes up. So we've got some fundamental validation that this temperature sensor is working in some ways that we understand about temperature. So what's our best estimate of what the actual room temperature is here? If you said our best estimate is 23.9, then I'd say you're doing pretty well, because that's the best information that we've got. It's consistent with the other information that we've got, and we haven't got any basis to make a different estimate than that. So we've got 23.9, but we know that it really could be different, the actual room temperature. And there are a bunch of reasons why this could happen. One is that I might have touched this before I made my measurement, and so it was reading too warm, and we'd have to wait a long time. Another would be typically manufacturing tolerances. If we make 100,000 of these, they won't all be exactly alike. They'll be pretty close. And if we put 100 of them side by side, I hope we'd get readings that were pretty close to each other, but they wouldn't be exactly the same. There is some variation there. None of these devices is perfect, especially an inexpensive little thermometer like this. So we've got manufacturing tolerances to take into account. And the thing is, we don't know the actual temperature. And that's important to remember, is that in most measurement situations, we don't know what the actual temperature T sub A is, or whatever other variable we're trying to measure. So all we can do is make our best estimate, and right now our best estimate is 23.9 degrees. And there's a pretty high probability that that actual temperature is really close to 23.9. So let's say the probability level around 23.9 is there. Now, as we get a little further away, the probability level might be lower. And if we get still further away, the probability level might be even lower. And finally, as we get really far away, the probability level's down to either 0 or almost 0. Now, if we drew a curve through these dots, we'd get something like this. And you might or might not recognize that as a bell curve or a Gaussian normal distribution. It's a distribution of probability that says the most likely values are in the center, and things get less and less likely as we go farther away. And if we drew some boundaries here so that 95% of the probability was inside, so if that represents 95% of all the probability, then this is the range of our uncertainty. So if it turned out that that was about 24.9 and 22.9, then we would say that our temperature was 23.9 degrees Celsius plus or minus 1 degree Celsius with 95% probability. And in this course and in most engineering measurement, we're going to use this 95% all the time. And as a result, what you'll see more commonly is just 23.9 plus minus 1 degrees Celsius as an expression of what the actual temperature is. And this is an expression of our uncertainty. We don't know what the actual temperature is, but we think that it's 95% likely to be within 22.9 up to 24.9 based on our measurement of 23.9. Now, where do we get that uncertainty? Well, it's not something we can know absolutely. It's something we can only estimate. And that's where we need to apply our engineering judgment. One of the sources for that estimation is going to be our experience. And I know you don't have very much experience, but you're going to get more and more experience. So experience tells me that plus or minus 1 degree Celsius is not an unusual level of uncertainty for a typical temperature measurement device. It's not bad. It's useful. Another place you can get it, if you're using a digital instrument, then you can make a good guess based on the significant digits. This one has 23.9, so it has one significant digit after the decimal. Now, usually when you have a digital display like this, they're making it only as high resolution as it needs to be to reflect what the instrument can measure. So there'd be no point, if this was plus or minus 1 degree, of having it 23.925437. All that extra precision isn't useful. In fact, I'm usually pretty suspicious of the quality of the measurement in that last digit on any digital display. So if I'm looking at a digital display, I'm going to pull an uncertainty just by saying it's this whole last digit. So that would be 23. Well, actually round up 24 or 25 or 23. So that would give me a plus or minus 1 there as well. Now that's just an estimate. Far better, instead of looking at those significant digits, is to go to the actual manufacturer's specifications. If you have a data sheet, then on that data sheet, there should be a manufacturer's specification that says what the accuracy they expect from their device is. So if the manufacturer says plus or minus 1 degree Celsius, then I would take that as being the 95% uncertainty case, even if they don't happen to mention this 95%. And the more information you can get from the data sheet, the more information you can get from the manufacturer, the better you can make that estimate of your uncertainty. Now, finally, if you really want to know what's going on, there's nothing left but to make some actual measurements. And if you're trying to measure uncertainty, well, you need to know the actual temperature. You can't tell how big a mistake you've got unless you know what the actual ambient temperature is. And then you can measure the error. And once you measure that error, which is just the measured temperature minus the actual temperature, that will tell you how big the error is in one measurement. And if you make that for many measurements, then this should come back to a distribution that looks a lot like that. If you measure a whole lot of error realizations, you'll get that distribution. You'll be able to figure out where the limits are for 95% of them, and you'll be able to pull out a much better estimate for the uncertainty associated with the particular measurement system that you're using in the particular conditions that you're using. Most of the time in engineering applications, you need to put an uncertainty on things. The place to go is go to the manufacturer's data sheet and take that plus or minus 1 degree Celsius. That'll tell you how accurate you are, and then you'll have to explore the consequences of that level of accuracy and whether or not it will change the decisions you make and the quality of your results based on that level of uncertainty. Every measurement you make in this course, every measurement you make in an engineering context should have an uncertainty attached to it. Saying 23.9 degrees Celsius doesn't tell me anything, or doesn't tell me enough anyway. You need to say 23.9 degrees Celsius plus or minus 1 degree or half a degree or 0.1 degree to tell me how accurate those measurements are. We'll look more in detail at how to measure this in some subsequent videos.